Welcome back to part 4 of our video series on triple integrals but round. We are talking about spherical coordinates in this one and how to do integrals in spherical coordinates. The first integral I want to do in spherical coordinates is, I think, the most simple. I want to find the volume of a sphere. We're going to find the volume of a sphere of radius 3, just so that we can ease ourselves into these integrals, and also so that we can check our answer easily, because we know the volume of a sphere of radius 3 should be 4/3 pi r cubed. So 4/3 of 27 is 36 pi. We should expect the answer of 36 pi for this integral, but I want to set it up first. Volume of a sphere of radius 3. So I want a triple integral. I want a better marker. Ugh. My markers are running out of good options for markers here. I'll get some new markers soon. We have a triple integral. I need a d rho, I need a d phi, and I need a d theta. And there's going to be some other exciting bits as well. Remember, in polar coordinates, we said that the volume isn't just, or the area isn't just dr d theta. We needed to add extra things into that piece so that we had a proper volume. And we ended up, in the end, we came up with r dr d theta, the Pyrrhic integrals. We had to add extra stuff. We have to add extra stuff to spherical integrals as well. Only one of these things actually has dimension. These two are directions. They're not going to help us out with anything. So we need to add at least 2 more dimensions to this to get a volume. And it turns out that what we add is rho squared sine of phi. You'll have to trust me on this one. I can make a compelling case for why we need to add an r to dr d theta to get an area, but rho squared sine of phi, this entire unit as a thing, this is my volume. So when you're doing spherical integrals, you can't. It's not enough to have d rho d phi d theta. You need to have rho squared sine of phi d rho d phi d theta. We need bounds as well. If I want a sphere of radius 3, then rho needs to go from 0 to 3. Phi is going to go from 0 to pi. This is the one that only goes 180 degrees. This is rho. And theta gets to go the full 360 out to 2 pi. This is the setup of my triple integral in spherical coordinates to get the volume of this particular sphere. So let's start integrating. Sine of phi is just going to function as a coefficient here. So I'm going to have the integral of rho squared d rho is going to be rho cubed over 3 sine of phi. We're evaluating this from 0 to 3. And we still have a d phi and a d theta. And we're still doing the integral phi from 0 to phi is pi. And back here the integral theta 0 to theta equals 2 pi. All these markers start out promising and then they're all faded and kind of crappy by the end. This is disappointing. Rho cubed, when I plug in 3, should give me 27 over 3 is 9. So this is theta from 0 to 2 pi, phi from 0 to 1 pi. This is going to be 9 sine of phi. D phi, phi looks like a D. D phi, that phi doesn't look like anything because my marker's dead. d phi d theta. So, the integral of sine of phi with respect to phi should be, theta is still going from 0 to 2 pi. Phi is going from 0 to pi. 9 gets to hang out. The integral of sine of phi d phi is negative cosine. So this is negative 9 cosine phi. Oh, I wrote this wrong. I'm not doing the second integral. I already took the second integral. Still have the integral for theta. Integral of this is negative 9 cosine phi from 0 to pi d theta. Now I need to start erasing some of these things. Or maybe I don't. Maybe I can squeeze this in. When you plug in pi into cosine of phi, you get negative 1. So this is going to be positive 9. When you plug in 0, you get positive 1. So this is 9 minus negative 9 integral from 0 to 2 pi d theta. So this is 18. The integral of 18 d theta from 0 to 2 pi. When you integrate a constant with respect to theta from 0 to 2 pi, you just multiply it by 2 pi. So this is 36 pi, just like we expected. So, the moral of this story is spherical coordinates, not so bad. They look like a hot mess. I'm not going to deny that. But don't be intimidated by their appearance. They're actually quite snuggly and very friendly. And you can use them to find the volume of spheres, which we already knew the volume of. So let's do another one. Let's see what happens when we do a triple integral of a density function. So I want the mass of a ball. I guess I should warn you. The homework uses the word ball a lot. Technically, a sphere is only like the outside shell of something, like the outside edge. If you have something that has like volume inside of it, like a filled-in sphere, the official geometric word for a filled-in sphere is a ball. So I don't know why they call it the volume of a sphere if the sphere is just the points on the outside, but I don't know. So I want the mass of a ball, radius 2, with density 1 over 1 plus rho cubed. So, once again, I need to set up this triple integral. The triple integral. The thing I'm actually integrating is this density function. 1 over 1 plus rho cubed. So this is something that is densest at the center and becomes less dense the further out you go. Uniformly less dense as you move away from this. This is the density function that I'm integrating. I also need to include rho squared sine of phi, because I always include this in all of my triple integrals in spherical coordinates. This just comes attached with d rho, d phi, and d theta. And now I just need bounds. If I want this thing to have radius 2, then rho needs to go from 0 to 2. Theta and phi are going to do the standard issue 0 to 2 pi on theta and 0 to pi on phi. So this is how I set up the mass of a ball with this density function and radius 2. Now that it's set up, all I have to do is integrate. Integrating this is going to be an exciting event because we have a bit of an inside-outside-other situation going on here. The inside, I'm going to say, is, please marker, don't let me down. The inside is 1 plus rho cubed. The outside is blob to the negative 1, and the other is rho squared. The sign of phi is like a coefficient. I'm kind of not worried about that. We'll just say rho squared d rho. We can effectively just move that to the outside. It's a coefficient on this one. So, when you integrate this, I'm going to need the derivative. Well, I'll set w equal to 1 plus rho cubed, and then dw is 3 rho squared d rho. So I need to put a 3 in here so I can swap this piece out with dw, and that means putting a 1/3 on the outside, and that's fine. And now they match. And I can do a nice clean substitution. And I'll end up with just w to the negative 1. That's the thing that I'm actually going to integrate in here. So I'm going to skip rewriting this a few times with all the pieces in there and just integrate w to the negative 1. The 1/3 stays on the outside. The integral theta goes from 0 to 2 pi. The next integral phi goes from 0 to pi. This integral, we said, is the integral of w to the negative 1. So that's going to be the natural log of w, 1 plus rho cubed. Sine of phi hangs out. This I'm evaluating at rho equals 0 and rho equals 2. And then I need a d phi and a d theta on the back end. So now I need to evaluate the natural log of 1 plus rho cubed at 0 and 2. This is one of those times, usually when we plug something in for 0, we just say, oh, it cancels. Just multiply everything by 0 and it goes away. We're adding stuff to it now, so we got to be real careful. Maybe it still cancels. Hopefully, we'll see. But we have to at least consider it. I'm going to start erasing up top, so I have room for this. I do not want, this is messy enough without me trying to write it small and get all crowded and stuff. Okay, so this is going to give us the natural log of 9. Well, I guess let me start from the left. Theta is still going from 0 to 2 pi. Phi is going from 0 to pi. This is natural log of 9 sine of phi minus the natural log of 1 sine of phi. And we did get lucky. The natural log of 1 is just 0. So when we plug in rho equals 0, this whole piece does become 0. Doesn't immediately, it's not immediately obvious that it'll be 0, but it works out that way for us. So this is just going to be the natural log of 9 sine of phi d phi d theta. So here's a little trick. Hopefully you remember from our volume of a sphere when we did that video. Hopefully you recall that when we integrated the sine of phi, it became negative cosine phi. Natural log is just a constant in this case. We could bring it to the outside if we wanted, and I probably will. But the integral of sine of phi is negative cosine. And when we plug in pi, we get negative 1 minus negative 1. So that's going to turn into positive 2. If nothing else is happening to the phi on this one, if you don't remember that, just rewind the video to where we did that part. I think we had 9. We had negative 9 cosine of phi, evaluating it at pi and 0. And the first evaluation turned into positive 1, and the second evaluation turned into another positive 1. So, actually, why don't I just do it on this one? I'm going to bring the natural log to the outside. 1/3 ln 9 on the outside, this marker. 1/3 ln 9 on the outside. Integral theta from 0 to 2 pi. Integral sine of phi is negative cosine phi from 0 to pi d theta. So, 1/3 ln 9. This is, I guess I still have a, theta still goes from 0 to 2 pi. Negative 1 minus negative 1. Plug in pi, we get negative 1 minus, plug in 0, we get negative 1. D theta. So generally speaking, if there's nothing else going on here, the integral sine of phi d phi from 0 to pi will always give you 2, which is nice. So this is, I'm going to bring that 2, this whole thing, this is equal to 2. I'm going to bring that to the outside, attach it to this 2/3. So 2/3 ln 9 times the integral, theta goes from 0 to 2 pi of 1 d theta, which we know is multiplied by 2 pi. 4 pi over 3 times the natural log of 9 is our final answer. So, these problems are long and complicated, and they get kind of messy, and there's a lot going on in them. But if you keep your wits about you and take it one little piece at a time, they're very doable. And if you do 4, 5, 6, 7 of them, you'll start to see the patterns, you'll get the hang of it, and things will go very nicely. There's still a couple more things that I want to talk about, so we're going to make a part 5 of this video series, so stay tuned for that.